Hi, this is Mrs. Villette, and this is a continuation of our videos on complex rational expressions. I'm going to show you another method now for simplifying complex rationals. It's called Method 2. Method 2 is to write both the numerator and denominator as single fractions with a common denominator and then divide the fractions. And I put keep, flip, change there so you could remember how to divide fractions. I'm going to show you this method on at least one of these problems, and then I'll let you decide if you like Method 1 or Method 2 better. So we have our complex fraction here, and what you really want to do is focus on the numerator and denominator separately. So just looking at the numerator, I can see that I have a common denominator of yz, and so I'm going to build each fraction to that common denominator. I will multiply this one by y over y, and this one by z over z. And that gives me 3y plus 2z all over yz. Now I'm going to do something similar with my denominator. It still has the same LCD, lowest common denominator, so this gives me 7y subtract 6z all over yz. Now we're going to locate the large fraction bar, and wherever that is, that's my division symbol. So I keep the top, 3y plus 2z all over yz, and I multiply by the reciprocal of the bottom. So I multiply by yz over 7y subtract 6z. Now we can see that the yz's will cancel, and I will get 3y plus 2z all over 7y subtract 6z. Now this is valid as long as y doesn't equal 0 and z does not equal 0. Also, if 7y subtract 6z does not equal 0. I don't think that your textbook will require you to list the domain restrictions on complex fractions, but it's always a good idea to go ahead and list them. I'm going to show that same problem with Method 2 instead. I actually prefer Method 2. I think it's a little bit faster. So same problem with Method 1. We find the overall lowest common denominator, which is yz, and I multiply by yz over 1 over yz over 1. The thing we need to realize here is we're not doing something drastically different. In Method 2, we were multiplying by a special form of 1. We were just doing it to each term in the fraction. So we multiplied this one by y over y, this one by z over z. That was a 1. Y over y, z over z is a 1. I'm also multiplying by a special version of a 1 here. It's just in the form yz over 1 over yz over 1. I want you to pay attention to what happens though when I distribute. So now I'm going to distribute from the right, and I get 3yz over z plus 2yz over y all over 7yz over z subtract 6yz over y. Doesn't actually look much better right now until we realize that a bunch of things cancel. So the z's cancel in the top left term, the y's cancel in the top right term, z's cancel bottom left, y's cancel bottom right. And now I don't actually have complex fractions anymore. I have 3y plus 2z over 1, so I don't need to write the over 1 part, and then 7y subtract 6z. Notice it's the same exact answer I got, and we need to, at the very least, list that the canceled factors cannot equal 0. So z cannot equal 0, y cannot equal 0. I'm going to go ahead and say you don't have to list this one over here because it's implied because the 7y subtract 6z is still in the denominator. So I'm a fan of Method 2, so this was, I'm a fan of Method 1. This was Method 2. Building and then inverting and multiplying. And then this was Method 1. I like Method 1. It seems a little bit cleaner to me, but both methods involve multiplying by a special version of a 1. So let's go ahead and take a look at example B. I'm going to use my preferred method, which is Method 1. And that would require me to find the overall LCD, which is just y. So I multiply by y over 1 over y over 1. If you think about what happens in the first term, you get y over y plus 2y over 1 over y, subtract 3y over 1. When the y's cancel, they leave behind a 1. So I end up with 1 plus 2y all over 1 subtract 3y, so long as the y value that I canceled was not equal to 0. So that was a pretty fast problem when we did method 1. The names aren't interesting enough for me to keep them straight. The second method would have been to instead multiply individual terms to get to the common denominator. So I would have multiplied here by y over y on the terms that didn't have the y. And then I would have 1 plus 2y all over y over 1 subtract 3y all over y. Hopefully you can see that when you invert and multiply, those y's would cancel and we'd end up with the same answer. Okay, the last problem is very reminiscent of something that we would see in calculus. This is called a difference quotient. You'll learn about that more when you get to calculus, but the algebra behind this problem is something that we're dealing with right now. What we want to first realize in this problem is no matter which method we do, we need to find the LCD. This is a complex fraction where only the numerator contains fractions. The denominator does not contain fractions. It may be helpful, however, to write this as h over 1. I'm going to identify my lowest common denominator. Looking at all my denominators, I have x plus h, x, and 1. X plus h does not factor, so I'm just going to put parentheses around that to show me that it's already factored. Since x plus h and x do not contain any common factors, the LCD is simply the product of the factors of the denominators, so x plus h and x. So for our method 1, we are going to multiply by the LCD over 1 over the LCD over 1. Now you can go ahead and squeeze it on to the front of your problem. You can do it on the left or the right. It doesn't really matter where you do it. So x plus h times x over 1 over x plus h times x over 1. And I distribute in the numerator, and that gives me 2 x plus h times x over x plus h. Subtract 2 x plus h times x over x all over h times x plus h times x. Now notice I have a 1 down here, but I don't really need that 1. One thing you want to be really aware of is you don't want to distribute these numerators. When we're using this method, the LCD that we choose should cancel out the denominators. So I have an x plus h and an x plus h that can cancel. I have an x and an x that will cancel, and now I no longer have denominators. So now I have 2x, subtract 2 x plus h, all over h, x plus h, x. Go ahead and leave those denominators factored. We do need to simplify the numerator. I'm just going to go in a little scratch zone over here. I have 2x, subtract 2x, subtract 2h. The 2x's cancel, and I get minus 2h over h, x plus h times x. There is a common factor that I can cancel of h, so long as it does not equal 0. We also have the requirement that x couldn't equal 0 and that x plus h could not equal 0. Now the x not equaling 0, I already know that. It's in my denominator. The x plus h not equaling 0, I also already know that because it's in my denominator. But this canceled factor of h is actually going to be gone in my next step, so I need to make sure if I'm doing good bookkeeping that I keep track at the very least of that one. So I get negative 2h over x let's just write it x plus h, as long as the h is not 0. And that's my final answer.